Now we are going to start chapter 2. This chapter is devoted to first order partial differential equation. The entire chapter is divided into 5 modules. In module 1 we shall discuss about some basic ideas of first order partial differential equation. In module 2 we shall discuss about first order quasi-linear partial differential equation. In module 3 we shall discuss about non-linear first order partial differential equation, and in module 4 we shall discuss about the Charpit's methods and Jacobi's methods for solving a first order differential equation, and in last module we shall discuss about solution of a first order differential equation satisfying some given conditions. First of all, let me explain why should we read first order partial differential equation. The first order differential equation is important because this type of equation arises in mathematical physics, chemistry, etc. in different fields, and this is easy to handle. Moreover, the concept of first order differential equation is useful to understand or study the higher order partial differential equation. So, now we are going to start module 1 and we are going to our first slide of module 1. We have classified a general partial differential equation in chapter 1. Now, we want to do this classification in the context of first order partial differential equation. The general form of a first order differential equation in two variables can be written in this form: capital F x y z zx zy equals to 0, where zx is del z del x and zy is del z del y. In standard notation, zx is denoted by small p and zy is denoted by small q. So, equation 1 is written as f x y z p q equals to 0. In the similar way, one can define a first order partial differential equation in 3 variables x, y, u in this form, which is written in equation number 3. Here x, y, u are independent variables and z is the dependent variables. Now, a differential equation, first order differential equation is called linear if it is linear in its derivatives. So, the general form of a first order linear differential equation is given by equation number 4, where small p and small q are respectively del z del x and del z del y. So, it is linear in z, zx and zy, and a quasi-linear equation is defined as a differential equation where the coefficients of p and q are function of x, y and z. So, the general form can be written in this way, which is given in equation number 5: a p plus b q plus equals to c, where each of a, b and c is a function of x, y and z. So, this is one of the example of quasi-linear equation: x into z minus 2 y square p plus y into z minus y square minus 2x square q equals to z into z minus y square minus 2x square, and zp plus q plus n z square equals to 0. This is also a quasi-linear equation. And the next type of equation is semi-linear equation. So, in the general form of a semi-linear first order equation, the coefficient of p and q are function of only independent variables x and y. But in case of quasi-linear equation, a and b may be function of the dependent variable z. So, this is one of the example of semi-linear equation. So, in both the equation, the coefficient of p and q are function of x and y only. And the most complicated type is the nonlinear equation, where the equation does not belongs to any of the three types which we have described already. So, these are the examples of nonlinear equation: p cube plus q cube equals to 3pq, q plus xp equals to p square. Now, I am going to discuss the origin of a first order partial differential equation. That means, from which problem a first order differential equation comes and what is the relation between a first order differential equation and its solution. In this regards, I want to mention that in case of ordinary differential equation, if there is a one parameter system of curves, then it corresponds to a first order ordinary differential equation. In case of two parameter family of curves, we get a second order ordinary differential equation. Now, we are going to discuss, is there any relation like that in case of partial differential equation? So, to get that answer, let us go to the next slide. Suppose we have a function and relation in the form f x, y, z, a, b equals to 0, where a, b are arbitrary parameters. Now, if we differentiate equation 7 with respect to x and y respectively, we will get the equation f x plus p f z equals to 0 and f y plus q f z equals to 0, where p equals to del z del x and q equals to del z del y. Now, from these two equations, if you eliminate a and b and substitute the values of a and b in equation 7, you will get a function and relation of the form f capital F x, y, z, p, q equals to 0. Therefore, the solution of capital F x, y, z, p, q equals to 0 is small f x, y, z, a, b equals to 0. So, in this case, the first order differential equation is formed by eliminating two arbitrary constants a and b. Let us take one example to explain it clearly. X minus a whole square plus y minus b whole square plus z square equals to 1. It represents a system of spheres with center at a, b, 0. Now, if we differentiate that equation with respect to a, x and y, we will get the relation x minus a plus zp equals to 0 and y minus b plus zq equals to 0. From these two equations, we can find the values of a and b, and if you substitute these values of a and b in the original equation, we will get a relation of the form z square into p square plus q square plus 1 equals to 1. So, this is the first order differential equation whose solution is x minus a whole square plus y minus b whole square plus z square equals to 1. So, in this case, eliminating two arbitrary constants a and b, we obtain a first order partial differential equation. There is another way to find a first order differential equation, which is elimination of arbitrary function. Suppose u and v are two functions of x, y and z where z is the dependent variable which is function of x and y, and the function u and v are related by the relation phi u v equals to 0. Now, if we differentiate phi with respect to x and y respectively, we will get two equations which are written here. Now, from these two equations we can eliminate del phi del u and del phi del v to get a relation of the form del u v del y z p plus del u v del z x q equals to del u v del x y, or in other words capital P small p plus capital Q small q equals to capital R, where capital P, capital Q, capital R has the expressions which are written in equation number 9. The equation 8 is called Lagrange equation of first order. So, in this case we find a first order differential equation by eliminating the arbitrary function phi. To explain the above procedure, we are taking this example. Let z is some function of xy by small z. Now, from this equation, if we differentiate it with respect to x and y, we will get two relation in the form p is equal to f dash xy by z into y by z minus xy by z square p, and q equals to f dash xy by z into x by z minus xy by z square into q. So, from these two equations we get the value of p by q in this form. That means, in the above two equation if we eliminate f dash x, then we will get a relation in the form px minus qy equals to 0, and this is a first order differential equation. So, in this case eliminating the function f, we are getting a first order differential equation. Now, we will explain what is the difference between the solutions of a first order differential equation. In the first case, we have shown that a first order differential equation can be obtained by eliminating two arbitrary constants a and b from a given function f x y z a b equals to 0. And so, this is the solution of a first order differential equation, and this solution is known as complete solution or complete integral. We have also shown that eliminating an arbitrary function phi u v equals to 0, we can get a first order differential equation. Therefore, a solution of the type phi u v equals to 0 is called a general solution of the given equation. There is another way to find general solution, in which we find the locus of a parametric family of curves, which is called the characteristic of the envelope of the family if x, y, z, a psi a equals to 0, where b is supposed to be a function of a. Now, we shall illustrate all this concept taking one example. So, before explaining that example, let us discuss about the singular solution. This is another type of solution, in which case we eliminate a from the equation small f equals to 0 and del f del a equals to 0 and del f del b equals to 0. And there is another way to find singular solution from the given differential equation capital F x y z p q equals to 0. From the given differential equation, one can eliminate p and q from the equation capital F equals to 0, del f del p equals to 0 and del f del q equals to 0, and that equation is the singular solution of the given differential equation. Now, let us take one example. Z square into p square plus q square plus 1 equals to c square, where c is a constant. And we have to prove that this is x minus a whole square plus y minus b whole square plus z square equals to c square is a complete integral of the given equation, and we have to find also singular integral and the general integral assuming b equals to a. So, the given relation is x minus a whole square plus y minus b whole square plus z square minus c square equals to 0. So, if we differentiate it partially with respect to a and b, we will get the relation x minus a equals to 0 and y minus b equals to 0, or a equals to x, b equals to y. From these two equations, if we eliminate a and b from the equation f x y z a b equals to 0, we will get the solution z equals to plus minus c, and this equation is a solution of the singular solution of the given equation. Alternatively, one can find this singular solution from the given differential equation capital F x y z p q equals to z square p square plus q square plus 1 minus c square equals to 0. So, if we differentiate partially with respect to p and q, we get p equals to 0 and q equals to 0. So, if we substitute the values of p and q in the given equation, we will find a solution z equals to plus minus c. This is a singular solution, and we are getting the same singular solution which we have obtained by eliminating a and b from the general solution. Now, we are interested to find the general solution making b is equal to a. So, the equation becomes x minus a whole square plus y minus a whole square plus z square minus c square equals to 0. Now, differentiating this with respect to a, we get small a equals to half of x plus y. So, if we put this value of small a in the equation small f x y z a equals to 0, we will get a function half of x minus y whole square plus z square minus c square equals to 0. So, this solution is the required general solution or general integral of the given first order equation. Now, we are going to establish a functional relation between two first order partial differential equation under which these two equations are compatible. Suppose we have two first order partial differential equations capital F x y z p q equals to 0 and capital G x y z p q equals to 0. Now, these two systems are said to be compatible if a solution of the former satisfies the latter and conversely. We also assume that the Jacobian of capital F capital G with respect to p q is not equals to 0. That means, we can find the solution for p and q from the equation 12. So, solving equations in 12, we get p as function of x, y, z and q as function of x, y, z. The condition of compatibility of equation 12 is that dz equals to p dx plus q dy is integrable, and it is possible provided it satisfies the sufficient condition of integrability, that means x dot curl of x equals to 0, where capital X is P Q minus 1. That is, if P into del Q del Z minus Q into del P del Z plus del Q del X minus del P del Y is equal to 0, or in other words, we can write the relation in the form Qx plus Pqz equals to Py plus Qpz. Now, differentiating the first equation of 12, that means capital F equals to 0, we get Fx plus Fp Px plus Fq Qx equals to 0, and the second equation is obtained by differentiating 12 with respect to z, Fz plus Fp Pz plus Fq Qz equals to 0. Now, multiplying the first equation by 1 and the second equation by P, and then if we add those two equations, we get the relation which is written in 14a. Similarly, differentiating the function capital G with respect to x and z, in the similar way we can find a relation which is written in 14b. Now, if we eliminate Px plus Ppz from equations to 14a and 14b, we will get a relation del Fg del Xp plus P del Fg del Zp minus del Fg del Pq into Qx plus Pqz equals to 0. From this equation, one can find the value of Qx plus Pqz, which is written in 15a. So, the value of Qx plus Pqz is 1 by j del Fg del Xp plus P del Fg del Zp. Here j is the Jacobian of the function capital F capital G with respect to the variable P and Q. Similarly, if we differentiate equation 12 with respect to y and z, we can get the relation which is written in 15b. Py plus Qpz equals to minus 1 by j del Fg del Yq plus Q del Fg del Zq. And using these expressions, if you substitute those in equation number 13, that means if we put the values of Qx plus Pqz and Py plus Qpz, we will obtain a functional relation between the function f and g, which is written here. So, if the function f and g satisfies this relation, we can say that these two systems are compatible. That means the solution of the function f satisfies the equation g, and the solution of equation g will satisfy the function f equals to 0. Now, we shall take one example to explain the procedure more clearly. So, this is one example. We have to show that xp equals to yq and z into xp plus yq equals to 2xy, these are compatible. So, there are two given first order partial differential equations, we have to prove their compatibility. So, to prove the compatibility, we will find the values of the box Fg in this way. The box Fg, the expression which is written here. So, where capital F is given and capital G is given. So, if you compute this, we will get the value of box Fg equals to 0. Thus, it indicates that the equation xp minus yq equals to 0 and z into xp plus yq minus 2xy equals to 0 are compatible systems. Therefore, in module 1 of chapter 2, we have given some basic ideas about first order partial differential equation. First, we classified a first order differential equation, then we have discussed the origin of a first order differential equations. We have defined different type of solutions like general solutions, complete solutions and singular solutions, and lastly we have discussed about the compatibility of two given first order differential equations. So, with this we are ending this module.